about TCP reliable data transfer. Before I discuss this TCP reliable data transfer, I think we need to discuss about reliable data transfer protocol. So let's assume that we have two machines. Machine A and machine B. So do it again. And this is the timeline increasing downwards. So here we have a machine A and we have a machine B, and this is the time increasing downwards. So remember what we want to talk about. We want to talk about two things. Number one, reliable data transfer protocols, and pipeline or pipelining. These are two very important concepts that I want to discuss with you. So basically, we are interested in reliable data transfer. And I just want to discuss some or develop this understanding of reliable data transfer protocols before discussing TCP's reliable data transfer mechanism. So let's start discussing a simple concept. So say a machine, whenever a machine has to send a packet, it takes some time to reach machine B. Obviously, say machine A has transmitted a segment, say segment number 1, okay? And in a general reliable data transfer protocol, whenever a machine transmits a segment, it starts a timer. The purpose of the timer is that machine A will receive acknowledgement from machine B before the expiry of this timer, right? So for example, let's consider this scenario. Machine A transmitted segment number 1, but the acknowledgement is either lost. This is one possibility. So in this case, the timer will expire, and this machine will automatically resend this segment number 1. So in this case, the sender will maintain a variable where it will store the segment number of the recently transmitted segment, and similarly, receiver will also maintain a variable here where it will maintain recently received segment number, the segment number of the recently received segment. So the first scenario is in this reliable data transfer delivery protocol, if machine A is sending segment number 1, and there's a possibility the acknowledgement has lost. In this case, the timer will expire, and machine A will automatically resend segment number 1. So upon waiting and waiting, if this, the acknowledgement is not received, the timer has expired, A will retransmit segment number 1. and will obviously initiate the timer. Okay, so now we assume a scenario that B sends an acknowledgement before the expiry of the timer. And the next time A will send segment number 2, and then so on and so forth, right? This timer is generally based on round trip time, RTT. This is, yeah. So this timer is basically, generally, is based on RTT, round trip time. This is the time, in the worst case scenario, is the time required to transmit a segment and then receive this acknowledgement. And it's not consistent, obviously. That's why we use estimated RT, and there are many variation of this timer. This we will cover in TCP. TCP timers in the coming lectures. So this mechanism where the machine A has transmitted a segment and acknowledgement is not received before the expiry of the timer. In this case, the A has to retransmit segment number 1 automatically. This is known as, this is called automatic repeat request. ARQ. Okay, so this mechanism where where the acknowledgement is not received or acknowledgement is delayed, right? The sender will automatically regenerate that segment whose acknowledgement is not received, is known as automatic repeat request, or ARQ. Now, there are different reliable data transfer protocols that we can discuss. Number one is stop and wait. ARQ. And I'm hopeful that you understand ARQ now, automatic repeat request. And then the second is the second reliable data transfer protocol is go back and ARQ, automatic repeat request. And the third one is selective repeat ARQ. So after discussing these reliable data transfer protocols, then we'll be in a position to talk about the reliable data transfer of TCP, and we'll see TCP is closer to either go back and or selective repeat, automatic repeat, or stop and wait, or is a hybrid of some of these protocols. So let's talk about this stop and wait first. So in the stop and wait automatic repeat request, when a sender transmits a segment, say segment number 1, it waits for the acknowledgement from the other side. And yes, when it transmits a segment, it initiates a timer, right? So for example, machine A has transmitted segment number 1, and now machine A will stop and wait for the acknowledgement. So machine A has transmitted segment number 1, and there's no problem with the acknowledgement. So in this case, the acknowledgement is received by machine A. And upon receiving acknowledgement of the first segment, machine A will transmit segment number 2. And then it will stop and wait for the acknowledgement of segment number 2. In any case, for example, if the acknowledgement is, for example, lost, for example, acknowledgement was generated by machine B, but acknowledgement has lost, or there is this delayed acknowledgement due to some reason, the acknowledgement is received at the sender, machine A, after the expiry of the timer. A will automatically initiate this ARQ mechanism, automatic repeat request, and will, in this case, will retransmit segment number 1. Okay, but there can be another case also, that is segment number 1 never reached the destination. For example, segment number 1 was transmitted by the sender, but segment number 1 has lost. In this case, obviously, there will be no acknowledgement from the receiver side. Machine B will not send any acknowledgement. So machine is waiting upon the expiry of round trip time, RTT or estimated RTT. It will automatically resend the segment number 1 in this case. Okay. So what do you think? What's the problem with such a mechanism? Stop and wait. Yes, right. Because in stop and wait, after sending a segment, A is waiting for its acknowledgement. And A will only transmit the next segment, say segment number 2, when it receives the acknowledgement for segment number 1. So this makes this communication process very slow. We won't be able to have the optimal utilization of the bandwidth. Why? Because at any point in time, we are either only sending one segment or there is an acknowledgement from the destination, considering the destination scenario, the other scenario from the other side. When you're paying, for example, fortune for your bandwidth, and if you're making a protocol, reliable data transfer protocol such as stop and wait, this will really slow down your communication, obviously. So then what to do? So let's talk about the other option that we have. So that is go back N, GBN, right? Okay, in go back N, what we do basically is, rather than maintaining one variable on the sender and the receiver side, we have a buffer. So we have a buffer. We have a buffer here on the sender side. Here we have all the bits that we want to transfer. And similarly, we have a buffer on the receiver side. Okay, so here we also maintain a size, which is n this case, that identifies that how many number of bytes we can, or say segment, to make it simple, we can transmit. So in this case, for example, we have 1, 2, and 3. So this means that based on the size of this, so allow me to call it window, I can transmit segment number 1. I can transmit 3 segments. I can transmit segment number 1. I can transmit segment number 2 without waiting for an acknowledgement. So segment number 2. So without waiting an acknowledgement, I'm also sending segment number 3. Right? So based on the size, this n of go back n, the size of the window, I can transmit that much amount of data or the segments. So what was happening in stop and wait? So after sending segment number 1, machine A was waiting for the acknowledgement. Upon receiving an acknowledgement for segment number 1, only then will transfer segment number 2. But in this case, in go backend, I'll be sending segment number 1, segment number 2, segment number 3. How many segments? It entirely depends upon the size of this n of go backend, the window, right? And then the sender can send a cumulative acknowledgement. So we can have acknowledgement 4. This means what? That the receiver or machine B has received segment number 1, segment number 2, and segment number 3, and machine B is ready to receive segment number 4. So what, upon receiving this acknowledgement, what will happen on the sender side? The sender side, now these segments have been acknowledged, right? I'm keeping it simple, or the bits have been acknowledged, right? And now I will move this window to the segments to be transferred, right? Say these are segment number 4, 5, and 6. So now this window, now this mechanism where we are sliding the window is known as sliding window, right? So we call it what? We call it sliding window. Okay, so upon receiving cumulative acknowledgement, we will move the window to the next segments or chunk in line that we have to transfer. So now here we are not sending one segment at a time. So what we are doing, we are sending segment number 1, 2, 3, 4, which entirely depends upon the n or the window, receive window size. Remember, we talked about this receive window size in the segment header of TCP that we said is dependent upon either the receiver buffer or the network congestion profile. Okay, so this is pipelining, right? So we are sending more than one segment depending upon the size. So we are sending segment 1, segment 2, segment 3. This is called pipelining, pipelined reliable data transfer. This is obviously more efficient than stop and wait in terms of bandwidth utilization, right? But here, the drawback with such a mechanism is that what if I'm sending segment 1, but segment 1 has been has lost, right? So let me draw it, make a new scenario for you to understand the challenge of such a scheme. So, for example, my transmit segment number 1, but segment number 1 has lost. Then I transmit segment number 2. Segment number 2 successfully received by machine B. Then I transmitted segment number 3. Segment 3 is also received successfully by machine B. So what we will do in this case, what acknowledgement will be generated by machine B? Yes, you're right. Acknowledgement 1. So B will say, okay, send me segment number 1. So what A gonna do is A will go back to N. A will go back to the lost segment, which is segment number 1. A will not only retransmit segment number 1, but it will also retransmit segment number 2 and segment number 3. So though the segment number 2 and 3 has been already received by the receiver. Okay, but since the segment number 1 is missing, the acknowledgement from machine B is acknowledgement 1. So the sender goes back to the lost segment, which is segment number 1. So it retransmits segment number 1, segment number 2, and then segment number 3, which is obviously consuming the bandwidth unnecessarily, right? So here again, we can have another scenario. For example, what if the acknowledgement is lost? What if B transmits segment number 1, segment number 2, and segment number 3, but the acknowledgement is lost? What will happen in this case? So the scenario that I'm talking about is okay. Machine A transmitted segment number 1, then segment number 2, and then segment number 3. So 1, 2, and 3, and acknowledgement was generated, cumulative acknowledgement, say 4, the acknowledgement is lost. Acknowledgement is lost. What will happen? So A is waiting for the acknowledgement is not received, the timer goes out, then again it will go back to the last unacknowledged segment, say segment number 1 in this case. It will retransmit segment number 1, then 2, and then 3, right? So obviously there is a performance constraint in this case, okay? So it can be improved with the help of selective repeat automatic repeat request. What it does is, SR, what it does is, for example, if A has transmitted segment number 1 received by machine B, and then it transmits segment number, so segment number 1 is successfully transmitted and received, but segment number 2 is lost, and then it transmits segment number 3, which is also received by machine B successfully. Now, this machine can send acknowledgement 2, which means machine A only needs to retransmit segment number 2 rather than going back to the lost segment, say segment number 2, and retransmit segment number 2 and then retransmit segment number 3. It would only retransmit segment number 2. And we can call it negative acknowledgement, where we will only identify the segment that is not received by the receiver machine. Now talk about the TCP reliability mechanisms. TCP ensures reliability in 2 ways. TCP also, maintains this, also uses this automatic repeat request. So let's try to understand with the help of a scenario. There are 2 ways in which TCP maintains the reliability. One is using automatic repeat request, as is happening in all of these cases, the different reliable data transfer protocols. And the other is by using duplicate acknowledgements. So TCP's reliability mechanism will be triggered either if TCP has transmitted a segment, say segment number 1, and segment number 1 is received by machine B, and machine B generates an acknowledgement, but the acknowledgement is lost. And whenever machine A using TCP transmits segment number 1, it generates an acknowledgement. It generates a timer, sorry. And if the acknowledgement is not received before the expiry of the timer, the timer goes out, and TCP using automatic repeat request will automatically resend segment number 1. This is one way TCP trigger its reliability mechanism. Okay, the other way is that TCP transmits segment number 1 well received by machine B, then it transmits segment number 2, but segment number 2 has lost. Then it transmits segment number 3. Now, B will not wait for the timer to goes out on the A or the sender side, and A will automatically resend segment number 2. Instead, B will, on receiving, let me extend it a little bit more clarity. B will send duplicate acknowledgements. What do we mean by duplicate acknowledgement? B will say, okay, fine, I need acknowledgement 2, means I need segment number 2. Segment number 2. I need segment number 2. So upon receiving 3 duplicate acknowledgement, the sender A will not wait for the expiry of the timer. Upon receiving 3 duplicate acknowledgement, sender will immediately resend segment number 2, the lost segment, segment number 2, right? So this is called the fast retransmit, because it will take time if sender waits for the expiry of the timer. If there are duplicate acknowledgements from machine B, machine A will immediately resend the segment and will not wait for the expiry of the timer. TCP also has, you can see, cumulative acknowledgement. So what do you think? Is TCP more closer to go back N or selective repeat? So this is another question for discussion in our live session that we'll be having discussion about. So I hope you will think about it. Okay, so if we talk about TCP reliable mechanism, so now we can understand what information is given here. So it has it's basically a pipelined reliable data transfer. Means we are sending segments without waiting for an acknowledgement, because the acknowledgement is cumulative. And how many number of segments we can transmit, it depends upon the receive window size, which is calculated based on the space available in the buffer or the network congestion profile. Okay, and there are 2 ways in TCP's reliability mechanism triggered. One is the timeout event, where the timer expires, right? Where the RTT goes out, the timer expires, right? Or duplicate acknowledgement. How many duplicate acknowledgements? 3 for a lost segment, right? And TCP is basically either closer to go back, and it seems like it's closer to go back N, or selective repeat, automatic repeat request. But I would like to discuss with you in our online session.